Okay, yes, so this is us, Introduction to Computational Statistics with R. This is my contact information. It's all on the course syllabus, and yeah, okay, this is my commitment to you. So you guys are the paying customer, you guys are the students, and it is because of you that I have a job, and so I'm very grateful for you guys enrolling in my course, and I want to keep you guys happy. And so, you know, if you feel like something is not going, like you're not learning in the course, you know, let me know, okay? And I'll try to work and tailor things. I'm pretty happy with what I'm covering in the class, but I'm always looking to hear ways to improve as a teacher, okay? As far as you guys, I expect you guys to wrestle with difficult topics and put forth a good faith effort as we work through stuff. Okay, so I expect you guys to come to class and you know, be ready to learn. Okay, so please, you know, you guys have your computers in front of you and everything. And I hope you guys use them to follow along and not, you know, check your email or browse the internet or do other things, okay? Of course, I know that when you bring your computers to class, they can be a distraction, but I ask that you try to pay attention, okay? I think you'll get more out of the class that way. All right, so what is computational statistics all about? And so maybe first if we can just back up and say, why do we bother studying statistics? And I argue that it is to gain a better understanding of the world around us. That can be said about pretty much any subject that we study, any of the sciences, soft or hard sciences, we try to study to gain a better understanding of the world. And specifically, statistics is about taking data and drawing insight from it. Okay, the hottest job in the market right now is data scientist, and that's this idea of we have data and we can draw meaning out of it. And I would say that's what statistics is all about. And we're effectively asking and trying to answer the question, what does this data tell me about the world? Okay, and so that's what we have. Probably in your intro stats class, you covered, you know, the idea of a p-value and the question of, could the data that I have, could this just be a random fluke, or is it actually something that is happening in the data, is something about the process revealing something, okay? And everything in intro stats, I'm kind of flying through this stuff here, was based on a theoretical concept, okay? You had the central limit theorem. That should have been a central tenet that you learned in your intro stats class. The central limit theorem basically said, whenever we're looking at means or proportions of some kind of population, we can model the sampling distribution with a normal distribution. And we said, because we know things come from a normal distribution, if the mean of my sample is 10, then, or if the mean of my sample is 11.3, then I know that the mean of the population has to be somewhat close by, all right? And you studied the normal distribution to try to answer the question, could I get a sample with a mean of 11.3 just by random chance if the population has a mean of 10? And based on the probability of that data happening, you were able to answer your question. Okay, and so that is, the setup there is based on kind of this theoretic idea that the sampling distribution follows a normal model, right? If the sampling distribution does not follow a normal model, then your method for creating confidence intervals and your method for performing hypothesis tests no longer work, right? And that's why this should have been covered in your intro stats class. You had to check conditions to make sure you could apply the central limit theorem, right? This is Kind of familiar? Yes? Okay. If you guys are sitting there, if just nod your head and smile. If so, and that nonverbal feedback just lets me know that you guys are following along here. Sometimes, however, we cannot use the normal model. Okay, sometimes the math to try to model a sampling distribution or whatever it might be that we're looking at, sometimes the math there is too complicated. Okay, and we can't use the normal model, we can't use the central limit theorem, there's all sorts of things. And so how do we answer those questions? Okay, and that's where use of the computer has really advanced or opened up our ability to answer some of these questions. Okay, so we can simulate things using the computer. We can do things like bootstrap and whatnot to try to answer some of these more complicated questions where the analytic methods fail us. Okay, and so if you were to go to grad school for statistics, there's probably a few paths that you could go down. Okay, and one is to focus more on the analytics side and do some heavy math to try to unlock certain ideas. And then the other is you could kind of go down the computational side where you don't necessarily dig into the math, but you try to answer questions via simulation. Okay, so and that's what this course is broadly about. Okay, it's using the computer and computationally intensive methods to try to answer some of our statistical questions. Okay, when we say it's not using R to just do data analysis, right? You probably took or will take 101A, which is regression analysis. Okay, and that's all done on the computer. Nobody does regression analysis by hand anymore. But that's technically not computational statistics. That's using R as a statistical platform to analyze your data using regression models and things like that. But that's technically not computational statistics. All of that, linear regression comes from more of a theoretic and analytical thing, right? You model in linear regression, you're modeling a linear relationship and you model the errors as coming from a normal distribution, and that's why in linear regression, to check to make sure everything works out, you check your residuals to make sure it looks like they're randomly distributed and things like that. So that's not computational statistics, that's doing statistics with a computer. This is about computationally intensive methods to try to answer tough questions. All right, thematically, this course is split into two parts. Some people have complained it feels like it's two courses in one, and I would say that's kind of by design. Okay, the first part is we're going to focus a lot on computer programming and using learning R and the tools in R, such as some of the packages that I think are useful. And then the second part will be the methods for computational statistics. So we'll cover things like permutation and randomization tests and bootstrap and things of that nature. Okay, and I said this is kind of like woodshop class. I don't know if you guys ever took a woodshop in high school or anything, but first you learn how to use the tools and then you do projects with them, right? And in woodshop, a lot of the time is spent on safety, and perhaps in our class we don't focus so much on safety, but maybe we should, okay? Because you can be dangerous with the computer. All right, so some of the tools we'll cover are Markdown, different packages, tidy, dplyr, stuff like that, okay. And then computational statistics, some basic numeric methods, and then simulation, things like that. Okay, you guys are all familiar with R Markdown? Anybody here not familiar with R Markdown? Okay, I'm going to just skip all of this then. Okay, so basically I'm going to post your homework assignments as R Markdown documents. You open that in RStudio, you manipulate it there, and then you submit it. Okay, if you were too shy to raise your hand when I asked about R Markdown, just turn to your neighbor, and I'm sure someone in the class can lead you through it. It's pretty easy. Okay, let's start digging into R itself then. Okay, this is data structures in R. And as far as data structures in R, we've got your one-dimensional data, and you're probably familiar with the vector in R. Okay, then you've got two-dimensional data, which will be the matrix, and then n-dimensional, you have the array. Okay, the vector matrix, atomic vector matrix, and array, those are all what we call homogeneous data structures, meaning that everything in that thing has to be of the same type. So if you're going to put number, you cannot, in an atomic vector, you cannot mix numbers and characters. Okay, you're going to have numbers in there. They all have to be numbers of the same type. So if they're integers, they all have to be integers. If they're floating point numbers, they got to all be floating point numbers, things like that. Okay, and then you can have heterogeneous mixed data types in a list, which is sometimes called a generic vector, or in a data frame. Okay, and so with a data frame, you've got a table and you've got columns. One column has numbers, another column has characters, another column has factors, things like that. And that's what we have. We probably, you know, these are the four. I mean, arrays are sometimes used, but less so. But these are your four types here. Okay. As far as the atomic vectors go, we have 6 data types. Okay, and you can call R and you just say type of. Okay. Let's see here. Let me. And you just run the command type of. Okay. So let's say you have the number 3, that's the number 3, and you could say type of, and you say 3, and it will say, oh, it's type double, okay? But then if you do like 1 through 3, you get the numbers 1 through 3, and you say type of, and this will say this is integer type, okay? And so the different types of data that we have, we've got logical, which will be true and false. We have double, which will be this is your standard number. Okay, anytime you tell R we've got a number, it defaults to using type double. Integers, the whole numbers. Okay, and then we have characters for all of your letters. We also have complex in case you're dealing with imaginary numbers, and then raw is like how things are stored in memory. We pretty much use only the first 4. Okay, logical, double, integer, and character. Okay, and we use the function type of. Maybe you guys might be familiar, maybe with the function class. Okay, or maybe not. Okay, class sometimes feels like we can use this, but a lot of times if you use class, it'll say numeric, which is not the same thing as a type. And then class, it's more for the object classes, so you have factors and things like that. Okay, but these are the 4 basic things. Everything in R, underlying at the very bottom. Okay, even if you have a factor. Okay, so even if you're dealing with factors, factors are actually integers. If you ask type of on a factor object, it's going to return integer. Okay, so everything in R, the type ofs, the data types, these are basically it. Okay, it's going to be stored as one of these 6, and most likely one of these 4. Those are your 4 types. Okay, so in atomic vectors, everything has to be of the same type, and so with logical, you know, we can say type of true, and it will say logical, and then false, false, whatever. Okay, vectors, atomic vectors of this are all logical. Okay. Whenever you use the words true and false, I strongly urge or recommend that you type out the words true, T-R-U-E in all caps, or false, F-A-L-S-E, in all caps, okay, rather than T or F, the capital T or F. Like R is smart enough to say like, oh, you gave me a capital T, I'm going to understand that this means true. But the words true and false in all caps, those are reserved words. So you cannot go around and change the values of true and false. So if I say, if I got true, I've got true. If I type in just capital T, R understands, oh, you mean true there. But I can also store the value 0 into T, okay? And then this is going to give me some problems, okay? Because if I say, you know, if T, then you know, we're gonna have issues there, okay? But I can't store the value 0 into true, okay? Because true is a reserved word. So, so same thing with T and F. So don't do that, okay? We got character strings. You know, you put things in quotes. R understands these are characters, okay? Otherwise, it's going to be looking for something, right? So if I say hello, R is going to say I don't have the object hello. But if I put that in quotes, then it says, oh, now we've got character strings. Okay, and here's a vector of character words. Okay. Your default numeric type, double means it's a floating point thing. This is kind of a borrowed term from like C. C had single and double precision floating point numbers. In R, there's only double precision floating point numbers. Basically, anything with that needs to have a decimal value is going to be stored as double, okay? So if it's 3.5, 3.5, that's going to be type double. But it's also the default type. So if you just say, I want the number 4, R defaults to using type double, okay? So if you say type of 1, 2, 3, it's going to say this is type double. It's ready to throw in decimal values here, okay? Meanwhile, if you want integers and say, I don't want decimal values, you put in an L, okay? You say 1L, and this is the number 1 as an integer with no decimal, and it's type integer. Okay. And if you use the colon, which is kind of the shorthand notation, give me all of the numbers between 1 through 3 or 1 through 100, whatever, those defaults to integer type, okay? Or not default, that creates a sequence of integers. You guys are familiar with the colon notation, right? 1 through, like for I and 1 through 100 or something like that, okay? You can combine vectors using the function C. So you just take things and you stick them together, okay? And it does this. I think you guys are familiar with this, okay? And then and you can always test for this, and you can say type of, and it will tell you what type it is. Or you could have is it logical or character double or integer or things like that, and that will return true or false, okay, in case you need to put this into a function or program that you're writing. Okay. All right, is integer 3, was that true or false? False, right? Because it's going to be type double. Is integer 3 through 6? True. Is numeric 3 through 6? This is true. Numeric is going to return true for integer or double, and then is double 3 through 6? False, right? Okay, so that's what we got. False, true, true, and false. Okay. Is atomic will return true if it's an atomic vector. Is vector will return true if it's any type of vector. So whether that's an atomic vector or a list, okay? So sometimes, so in our head we think we separate lists from vectors, but unfortunately in R, lists will return true if you ask is vector. Okay, I think you guys are familiar with this concept of coercion also, meaning, you know, R is dynamically typed, so versus a language like C where you say, where you declare everything and you say this is going to be type integer type and this is floating, you know, double precision floating point, and then it will return errors if you try to stick anything other than that into that location. R is dynamically typed. You say, I want the number 1, and I want to combine it with the character string hello. R will coerce the 1 into character type, okay? Because when you use the function C to combine things, everything has to be of the same type, right? You can't have integers mixed in with characters, and so R will coerce it, okay? And it doesn't complain, and it just does this, right? And it's always going to coerce to the kind of the least specific type. So, so here, if I have false with an integer, it's coercing it to an integer, which means false gets coerced into a 0, and then the 1 remains a 1. Okay. And over here, I've got a type double, something with decimals, with a number. It's with an integer. This is going to get coerced into something with decimals here. Okay, and so this looks at the least restrictive form and coerces all of the objects into that form. So logical is the most restrictive, then integer, then double, and then character, okay, which will be the least restrictive. Okay, so here I've got the logical, which is true, false, true, I for integer, D for double, and CH for character. Okay, so if I combine L, I, and D, this type, okay, true, false, true, the logical, the integer, and the double, and they're all going to get coerced into type double. So the logicals get converted into 1, 0, 1, and then the integer gets converted into type double, and then the 5, 6, 7 are all coerced into double. Okay. Meanwhile, if I coerce the logical, the double, and the character together, okay, it's going to coerce everything into a character, which means the true, false, true gets coerced into true, false, true as characters, and not 1, 0, 1. Okay. So if you understand why it ended up this way and why it ended up this way, then you are in good shape for understanding coercion. Okay. If this doesn't quite make sense, you know, in your notes, star page 35, and then just play around with this idea of coercion on your computer. Okay. Just the nature of this course, okay, I'm going to be covering a lot. Some of the things will not make sense the very first time you see it, okay? And that's totally okay. Just put a little star in your notes, just say, hey, look at this page again in the notes, and then in your own time, go back on the computer and just start, you know, typing in some of these things into the R console until it kind of makes sense, right? See if you can type something in and then predict what R is going to output, right? So if you say, okay, I want to combine, I don't know, the logical with the decimal type or the double type, you know, what's it going to output? Things like that. Okay. All right. And there are functions that explicitly coerce. So you say something like, take this logical vector and I want you to force it into numeric. So you say as.numeric, okay? And then you can do, and then when you have functions like sum says add these things up, okay? It's automatically going to coerce the logical vector into zeros and ones and add them up, and it returns 1. And then if you do mean, it's basically adding them up and dividing by how many you have, and so it gives you a proportion. And so maybe this was a trick that you guys used in Stats 20, maybe not. You just have a logical check, right? And you can just say, give me the mean of some test. Give me the mean of, you know, the vector gender equal to male or something like that, right? Equal male. So that's a logical test, right? If you say, if you got a vector of gender types, okay, a vector containing gender information, so you know, maybe male, female, other, or you know, did not specify, whatever you want to say, you might just say, okay, well, how many people reported male? And you can just do gender equal male, and that would return a vector of trues and falses. But then rather than having to then count those up and things like that, you can just throw it into mean, and you can get a proportion of people who self-reported male, something like that. Okay, so that's kind of a little thing there. Okay, coercion happens automatically. Okay, and a lot of these things just automatically do that for us. Okay, the explicit coercion does this when you say, I want this to coerce this as a logical or character or integer. Okay, so when you do logical, basically zeros will become false, everything else becomes true. Characters just turn it into characters, and then integers will just truncate. Okay, and then R does its best. Okay, but then it can't always do it, right? So it's not smart enough to understand natural language parsing when you do as.double the word one. It's going to say NA. Okay, NA means a missing value, right? And there are different NAs for different vector types. Okay, so if you start off with NA, it's going to return logical. Why do you think the default NA is logical? Yeah.
Because that's the most restrictive.
It's the most restrictive type, right? So if you have a logical vector of trues and falses, and one of those is a missing value, you can stick in an NA, and it will remain logical type, right? Whereas if you have a vector of double, okay, you've got a bunch of numbers in there, and then you stick in an NA, then what happens? That NA gets coerced into the less restrictive type of type double. Okay, so you got a bunch of numbers, the NA gets coerced, and so basically we start off the NA as the most restrictive type. So if you stick NA into anything, it's not going to coerce the other values to type character or something like that. Okay, and there are like NA types, and I don't know, is it NA underscore, yeah, like NA underscore character is there. So so normally if I did like true and NA, this will be this, and I say type of, this is going to still be type of logical, right? But if I say, if I use the character NA, which is the NA that's specific for character type, then it will get coerced into character type. Okay. So that's what ends up happening. And you can access the other types by doing NA underscore, and you can see the other stuff, but we rarely use those, right? Okay. Okay, other values, we've got NaN for not a number, and then positive infinity and negative infinity. Okay. Behavior is not always as expected. Basically, you want to try to avoid these in your mathematical operations. Okay. So, and this is not. Don't use R to try to answer your questions about difficult math concepts, right? Like, if you do 0 divided by 0, like, do we know how to answer that in math? Like, we don't know how to answer that in math, and don't try to use R to answer that, right? What's positive infinity plus negative infinity? Don't use R to answer these questions. Okay, we'll skip this quiz. I don't know. Do you guys care? No. Okay. Go to page 43 on your own time, and then see if you can answer these things. We got a lot of stuff to cover. Okay, element-wise operations. So you do things like addition, and you do things like multiplication, and R will do things element-wise. So if you take 1:4, which is the vector 1 through 4, and you take the vector 2 through 5, 2, 3, 4, 5, and you say add these two together, it's going to match up the first element with the first element. So it's going to do 1 plus 2 gives me 3. And it goes to the next one, 2 and 3 adds together to 5. And it goes down and it lines them up. And you get this, okay? Same thing with the multiplication. It kind of goes, it matches the first element with the first element, second element with the second element, third with the third, so on and so forth. And it does these operations, okay? If R runs out of one vector, okay, it's going to recycle the elements. So if it goes, he got 1 through 4 over here, and then just the numbers 2, 3, it's going to first do 1 times 2, then it goes to the second element, 2 times 3, and then now it's run out of elements in this vector. So in the first vector, it goes to the 3, and then it recycles back to the 2. Okay, and it does that, and then it goes to the 4, and it matches the 4 with the 3. Okay, and so actually, when you do stuff like 1 through 5 plus 4, what it's doing is it's taking this vector of 4, and it's recycling the 4 for every single element. So it's adding 4 to every single one of these. Okay. However, if they are of different lengths, R is going to complain, right? So you've got 1 through 4, and over here I have got 2 through 4. So it goes, so it matches the 1 with the 2 with the 3 with the 4. Then it recycles around, and it says 4 gets matched with 2, and it goes, huh, that's funny. Are you sure you meant to do this? Because I stopped at the 2, and I still had some numbers left over. So it's going to say, warning, longer object length is not a multiple of the shorter object length, okay? But it still does it. It says, I did my best. I'm not sure if this is what you wanted, but you are the operator, so I will do what you ask me to do. And that's what it says. Sometimes this is not what you want it to do. Sometimes you don't want it to do recycling, but that's R's default behavior. And if it is a multiple, like maybe you didn't want this, but if it is a multiple, it's not going to complain. It's just going to go ahead and do it, and it's not going to give you any kind of warning. Okay, warnings will not break your programs. It just spits out warnings. Okay. Are there any questions? Okay. You know, if I know this method isn't the best way to teach computer programming stuff. The best way to learn is to just try things out on your own. And if you find yourself falling asleep, you know, you can stand up and you know, stand up in the back or whatever. You know, do what you need to do. Okay. Okay. Here we got lists. Lists are generic vectors. They are one-dimensional, and they can contain any combination of our objects. Okay. And so here, I'm taking a character element, a logical vector, a type double, and a function. And these are all stored in this list exam, okay? And it says, okay, in the first position, I've got A, and then in the second position, I've got this logical vector, and in the third position, I've got the double vector, and in the last position, I've got a function. Okay. So lists just let you kind of stick things together. You can ask R for the structure of the list, okay? And it will say it's a list of 4 things, and this is what I have there. Okay. And it says I got a character, logical, and a numeric, or in this case double, and a function. Okay. Lists can be nested inside of lists, okay? And so here I've got the list B and the list C. List B is elements 5 and 12, and list C is 13, the object 13. And then if I put them together into another list A, then A looks like this, okay? It says the first object in A is a list itself, okay? And within that list, I've got the 5 and then the 12. And then the second object in A is another list, and that first object part in A, the second list is 13. And so when you ask for the structure of list A, it's going to say I've got 2 elements in A, and the first element is a list itself is a list of 2, and the second element itself is a list of 1. Okay. Things get a little bit can get weird. Okay. So here I'm saying take a list, and the list is 1, 2, and 3, 4. Okay. And so when we ask for the structure of X, it says it's a list of 2 things. The first thing being the list of 2, which is the 1, 2, and then the second thing being the numeric vector of 3, 4. Okay. Whereas over here, what happened? Okay, I have Y, and I didn't use list. I used C. I said combine the list 1, 2 with the elements 3, 4. What's happening is these elements 3, 4 get coerced into the list type, and so we end up getting a list of 4, 1, 2, 3, 4. Okay. Again, first time you see this, it feels funny. It's easy to confuse, get mixed up on how a list is going to behave when you start combining lists with other lists, or start using C to combine elements, or try to combine lists together. I put this up here as an example, not fully expecting you to absorb everything this first time you see it, okay? Definitely part of learning in the course is to play around with things on your computer. So I recommend putting a little star, page 52, and just play around with things and see what happens, okay? With lists, we can often name things in the list, okay? And so in the example list, we can say A is equal to the element 1, B is equal to this, and E is equal to this, okay? And thus, when we ask for these things, we can use the $ notation to kind of get at the object there, okay? So if I say, okay, I've created this list called examp, okay, which is a list of 3, and it says, okay, what is element A in the example? And it's going to say, okay, that's the number 1. And we ask, what's B? B is going to return a list of 2 items of C and D. Okay. If I directly reference element C from example, it's going to say that thing does not exist. Okay, it returns a null object. Okay. If I want that thing, I have to say, look at element B inside the top level example, and within B, look at element C. Okay, so it's got examp $B $C, and there we go. And then examp $E returns back kind of the third object there. Okay. So you can kind of drill down into elements of the list using this the $ notation there. Okay. Okay. Attributes. Attributes are arbitrary metadata that can be attached to objects in R. Okay. Some attributes are special, such as class names and dimension, and change the way the object is handled by R. But it could be anything. Okay. Attributes are anything that you can attach whatever you want to any object in the attribute. Okay. And you can access the attributes using the function attr or attributes. Okay. So here I'm creating a atomic vector X consisting of the elements 1, 2, and 3, and I'm giving them labels L, M, and N, or names. Okay. And so when I ask for what are the attributes of X, it returns back and says, okay, you've got this thing called names, and inside that I've got L, M, and N. Okay. If we ask, what is the structure of this thing? Attributes. The attributes themselves are a list. Okay. We can use the function attr and just say, okay, look up the attributes in X, find anything that's called names, and it's going to return back what we have there. Okay. But so often attributes that we have that are most commonly used are probably the names and the dimensions and the class. But again, you can store whatever you want, okay? You just say, I'm going to create a new attribute. This is called my_attribute. And in that thing, I'm going to just store this information. This is a vector. Or if I want to store something else here, right? Basically, it's a list, and the list can combine it pretty much have it anything you want, right? You want to store a function here, that's fine, you can do it, okay? Probably not the best usage, but basically, it's like you've got this object here, and then it's like you've got some, I don't know, an instruction manual or some documentation for that thing called attributes. And on this thing, you can store whatever you want. And so probably the most common usage is names, but again, anything you want to store there, you can, okay? Secret messages. It's allowed. However, most attributes are lost when the vector is modified, okay? The only attributes that are not lost will be names, dimensions, and class, okay? All right, and then these three attributes, you can get them, we have like shortcuts for them, and we can just say, what are the names of X, what are the dimensions, and what is the class of X, okay? Instead of having to write it out this way. So we can just say, okay, X, what are the attributes there? Okay. And then as soon as I modify X, okay, if I subset X using bracket 1, and we ask what are the attributes there, my bonus attribute of my attribute, that drops out, right? This thing goes away. The names are preserved. Okay. You can, multiple ways of naming a vector, okay? And this is what we have. We've got X. You can create it when you can have names when you create it, or you can modify a vector in place, okay? Or you can create a copy of it, okay? So you can say, so this is, I probably use the second method, the most common, right? So if I say X, I'm going to be the vector 1 through 5, okay? X here is 1 through 5, and I can say, what are the names of X? And right now I don't have anything there. But I can say, all right, what I want are the first 5 letters to be my, whoops. No, not the function subset there. Okay, and then so I can ask names of X are A, B, C, D, E, and if I ask X, it spits out 1 through 5 now with their associated names. Okay, so I can say, okay, X, give me what C is, okay? Or I could say, give me the 4th element or something like that. Okay, so we have names there. We have factors. Okay, we can use factors, and factors are basically when you are doing some kind of experiment or something, and you've got like different levels, right? And you say like this plant is going to get will be the control group, and this plant gets treatment 1, and this plant gets treatment 2, or something like that. And so you only have these 3 levels. You can store that in the factor, okay? And so rather than in your Excel worksheet, instead of having to say control, 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 treatment 1, treatment 1, treatment 1, and treatment 2, treatment 2, treatment 2, you can say kind of level 1, level 0, level 1, level 2, or something like that, okay? And that's basically what we're doing here, okay? Here, I'm saying create a factor out of this character vector, A, B, B, A, okay? And it does that, and then it says, okay, we are storing the levels A and B, okay? When we ask what is the class of this object, X, which is a factor, it's going to say it's a factor, okay? But if we ask the type of, underneath it, it's being stored as integer type, okay? And then the levels associated with X are the labels A and B, okay? So let me just, we'll say if I write control, treatment 1, treatment 2, and control, okay? Oops. So this is a character vector, but I can say make a factor out of this. Okay, and so X is a factor here. And if I say type of X, it's actually integer type. So if I force this into integer type and I say as.integer X, it's going to say 11231. Okay? Let me see. Let me make the text bigger here. Okay, so that's what we have here. Okay, and if I ask for the levels of X, okay, this is what I have. So what I can do, you know, I could rename this. And change the kind of the levels in this thing, because at the base, the storing underneath this are just the integers 1, 1, 2, 3, and 1 for control, treatment 1, treatment 2, and control. As.character X suddenly turns it back into characters, and that's what we have here. But it's important to note that the factors are stored as integers. Okay. If so, in this example, we have levels A and B, and if I tried to insert the value C in there, it's gonna say you can't do that. Okay, you can't put in something that the levels aren't there. Okay, and if you try to combine two different factor vectors, it's going to complain. Okay, because here it sees the A, and when it turns it into a factor, it stores it as the integer 1. And over here, because this is a separate factor, it sees the letter B, and it stores it as the integer 1 there also. And so when you combine those, it's sticking the 1 and the 1 together. And this is probably not what you were expecting, or this is probably not what you wanted. So, so you can't do that. Okay. If over here, you know, I've got this character vector for that has 3 m's in it, okay? And if we were going to create a factor for the sexies, we might define the levels that are available as m and f, okay? Maybe we would want another option there, but when you do this and you say create a table of this with the character vector, it just says, okay, I just see 3 m's. I see m3 appear 3 times. Whereas if you say make a table with the factor, it's going to give you, it's going to say I saw the m 3 times and I saw f 0 times, because it understands that other levels exist even if they are not observed in the data. Okay. A lot of times when you read in data, okay, and if you use read.csv, in your stats 20 class, how did you guys import data? Did you use read.csv, or did you go straight to reader and use that? You use read.csv? Okay, but did you also use readr? No? Some people are nodding. Okay, maybe not, I don't remember. Okay, well, read.csv is kind of the importing method in base R, and it defaults to converting strings as factors. Okay, this was probably a useful thing to do back in the day when memory was limited. Okay, and when you stored character information, it took up a lot more memory, and when you stored things as factors, it took up a lot less memory, because all you had to do was store the integer value and then the kind of the corresponding level information separately. Today, now that we got 16 gigabytes of memory on your laptop, this is not an issue, and defaulting to convert strings into factors is can often cause headaches. So I would recommend whenever you do read.csv to include the argument strings as factors equals false so it doesn't do that, okay? But I don't know, maybe that's what you want it to do, okay? Factors often look and behave like character vectors, but they are integers, and so when you turn things into strings, you can coerce them into strings, and it will often work fine. But if you do other things, it's going to use the underlying integer values. Okay, so anytime you're going to do a string operation on a factor, you want to explicitly convert it to a string first, and then do those operations. Okay, if you want to do integer operations, I would say explicitly turn them into integers and do those operations, rather than trying to do operations directly on the factors themselves. Okay, let's see. We got to we're like halfway through here. Okay. All right. Now I'm going to start talking about matrices and arrays. These are the two-dimensional atomic or the n-dimensional atomic vectors. Okay. So with matrices, everything has to be of the same type. So you cannot have a matrix where you've got some letters in this column and numbers in another column. Okay. If you want something like that, you have to use a data frame. A matrix, everything has to be of the same type. Most likely a number, that's where the matrices excel the most, but you can have character matrices and logical matrices as well. And this is what we have. Basically, it's just a new atomic vector with a dimensional attribute. Okay, so here we take an atomic vector 1 through 6, and then we attach the attributes, the number of columns and the number of rows, and then that's going to produce a matrix here. Okay, and then the default order in which R fills out the matrix is it fills out the first column, then the second, and then it fills them out column-wise. Okay, so it goes 1, 2, 3, 4, 5, 6. Okay, you can create an array with a vector to describe all of the dimensions. Okay, so this is going to have 2 columns, 3 rows, and 2 sheets. Okay, so it goes 1, 2, 3, 4, 5, 6. Okay, this is I'm sorry, 2 rows, 3 columns, and then the second sheet over here. Okay, so you can see kind of to indicate 1 comma to indicate the first column or first row, comma 1 to indicate the first column, and then comma 1 to indicate kind of the first sheet, and over here the second sheet. Okay, if you had another dimension, you'd be dealing with like the first prism and the next prism, things like that, right? Okay. You can modify an object in place by setting the attribute dimension. Okay, so 1 through 6 is going to just be an atomic vector, but then I'm going to modify dimension to say I want 3 rows, 2 columns, and then it modifies it right there in place. Okay, or I could just say take C, which is still, which is this thing here, which is the matrix, and say I want to turn it into a matrix with 2 rows and 3 columns, and we get this. Okay. You have the function length, which tells you how long an atomic vector is. This will generalize to the number of rows or the number of columns for a matrix, okay, or dimension for arrays, okay. And then names, you have row names and column names for matrices as well. So we can set this. So A is going to be a matrix with elements 1 through 6, and we can set the row names and we can set the column names. And that's what we have there. Okay. So if we ask for the length, the number of rows, and the number of columns, the length of A is 6, and then we've got 2 rows, 3 columns. And here I've got an array, and same thing, okay? Length of 12, all of these dimension names, whatnot. Okay, you can combine matrices or arrays using cbind and rbind, okay? Column binds by columns and binds by rows, okay? And you can transpose a matrix using T. And you can ask, is it a matrix or is it an array, or things like that. So if I bind A by columns, it's going to produce this. And if I bind A by rows, it's going to kind of just stack them on top of each other. Okay. You can have, so vectors are one-dimensional, okay? Or basically there's no dimensional attribute for a vector. But you can also have a matrix that's a single row or a single column, okay? And they behave a little bit differently, okay? So over here, this is just the vector f, 1, 2, and 3, okay? And if we ask for the structure, it's going to say integer, and the attributes, there's no attributes here, okay? On the other hand, I can take G, and this is a matrix, okay, of the elements 1 through 3 with 1 column, and it prints out like this, okay? The structure of G, we'll notice, is type integer, okay? And it will say it's got 3 rows and 1 column. So you notice there is a kind of a dimensional attribute here for the integer type, whereas over here it just says there's 3 elements and those are it. Here it's got 3 rows, 1 column. If we ask for the attributes of G, it says we have a dimensional attribute with 3 in the first thing, saying 3 rows, 1 column. Is atomic, you don't see it here, but it's true. Okay. If I do the same thing with a row matrix, we have this, okay? And again, the structure reveals the fact that we have a comma here reveals that there's 2 dimensions, okay? Versus the structure of the vector, there's no comma there to indicate that. And likewise, here's an array where there's no, there's only 1 dimension, right? And here it says so when we ask for the array. Okay. As far as data frames go, okay, data frames are effectively a list, but there are with a two-dimensional structure, okay? And so that basically just requires all of the elements in the list to be vectors of the same length. Okay, and now we still have these kind of the same properties, names, column names, and row names, and things like that. If you ask for the length of a data frame, it doesn't tell you how many elements there are. So when you ask for the length of a matrix, if it was a 10 by 10 matrix, and I ask what's the length of the matrix, length would tell me what? 100, right? If it's a 10 by 10 matrix, it would tell me you've got 100 elements in that matrix, 10 rows and 10 columns. If you have a 10 by 10 data frame, okay, you've got 10 rows and 10 columns, and you ask for the length of the data frame, it's going to see it as a list of 10 things, okay? It's a list of 10 elements, and each element is a vector of 10 elements, okay? So if you ask for the length of a data frame, it's going to return 10, okay? So effectively the same as number of columns, okay? And you can subset a data frame like a one-dimensional structure where it behaves like a list, or you can subset it like a two-dimensional structure where it's going to behave like a matrix. Okay, so here I'm creating a data frame, 3 rows, 2 columns, and basically imagine this as I could have just written list 1 through 3, you know, and done this, and I would have got something similar, except I wrote data frame, and so it prints it out in like a matrix here, okay? And if I ask what's the structure of data frame, it's going to say, okay, you've got 3 observations of 2 variables, basically a list of 2 things. X is the first thing in that list, is the first, and Y is the second, and this is what it produces here. Okay. So it defaulted. One thing you notice is that when we created a data frame, it didn't treat this as character, right? It defaulted to treating this as a factor. Okay, and so if you want to treat it as character, you probably have to say strings as factors equals false. So that's one thing to note. When I created the data frame manually here, it defaulted to treating it as a factor. Okay, yeah, again, I write that here. Okay, so if I said strings as factors false, then it will treat it as a character. Okay. Okay. If I ask what is the type of for DF, it's going to say it's a list. Underlying everything, at the base of everything, a data frame is a list. Okay. However, the class, the object type, is a data frame. Okay. And you can say, is it a data frame? And it's going to say true. You can coerce things into data frames. You can say as.dataframe, and you can coerce a vector. You can coerce a matrix and things like that. Okay, a list will create 1 column for each element, but if they're not all the same length, it's going to produce an error. Okay, you can take data frames and combine them using cbind or rbind, like we did with matrices. Okay, so df, if you remember, is this this data frame here. We just got 1 through 3 in ABC, and so I've got that there, and then I can bind it with the third column, 3, 2, 1, Z. Okay, I can rbind using another data frame where X is 10 and Y is Z. Okay, and here I have to kind of name these elements for to add a row. Okay. So when combining column-wise, the number of rows must match, but the row names don't matter. Okay. When combining row-wise, both the numbers and the names of columns must match. Okay. So here it's important that I used X as 10 and Y is equal to Z when I'm adding a row there. Okay. Because the idea here is you're kind of like merging these tables together, and if you've got different things, it's going to complain, right? So if you're trying to do some data and mix things together, you just want to make sure things match up correctly. Okay. It's a common mistake to try and create a data frame by using cbind with vectors. Okay. This isn't going to work because cbind is originally a matrix operation. So when you do the vectors and you use cbind to vectors, what's it going to do? It's going to coerce everything to be of the same type. Okay, so if you want to do something like that, just use data frame directly. Okay, so if I tried to do cbind 1 through 2 and elements A and B, the characters A and B, or in this case a factor, first it coerced everything into letters and then it combined them. Okay, so this is not what we want. Okay, what you want to do is you just want to do data frame directly. Okay, and you do 1 through 2 and then A and B, and then it creates it probably the way you want it. Okay, later on in the class we'll use the package dplyr. Okay, and there's something called a tibble or table df, which is identical to the data frame, except when it displays on the screen, it is smart enough to only print out what's going to fit on the screen. Maybe you've experienced this thing where you type in the name of the data frame and R tries to print out the entire thing, right? Maybe there's 10,000 rows and it suddenly just flushes out everything in your on your screen there. Okay, if you put table df, it's not going to do that. Okay, that's those are the kind of the data types. I'm pretty sure you're familiar with a lot of those things. Here in this class, we're covering things at a little bit of a deeper level, and I'll post kind of your first homework assignment today, and it'll just have you kind of mess around with these things at a deeper level. I want to talk about subsetting. Okay, subsetting allows you to take a large data structure and then just pulling out the pieces that you want. Okay, and so that's what we're going to talk about here. Okay, I think when you are new to R, your subsetting skills are probably on the weaker side. Okay, as you get better with R, this is probably one area where your skills get stronger. Okay, okay, so there are several interrelated concepts. We've got 3 subsetting operators, 6 types of subsetting, important differences in behavior for different objects, whether they're vectors, lists, factors, matrices, and data frames, and the use of subsetting in conjunction with assignment. Okay. Again, structure, STR, is an important way to kind of know how to properly subset things. Okay. All right, so we'll cover subsetting using the bracket for atomic vectors, and then we will expand using subsetting using the double bracket and the $sign for lists and things of that part, and we'll kind of look at some of these things. I probably won't get to cover everything in our remaining 30 minutes, so I'll leave it to you to do your reading and kind of just make sure you understand all of these subsetting things. Oh, one thing I didn't really say, but as far as textbooks in this class go, we are going to use several textbooks. However, all of them I've tried to pick out ones that are all free. Okay, and so if you take a look at the syllabus, and you should be able to access all of these textbooks for free as long as you're connected to the UCLA network. So if you're at home and you live off campus, you're going to have to VPN into the UCLA network, and then you should be able to download all of these textbooks for free. Most of them are from CRC BaseNet, and actually 2 are from CRC BaseNet. One's from Safari Books Online, and then the other is from Wiley Online Library. They're all available free to UCLA students. So all of this stuff is coming, today's stuff is coming from a textbook called Advanced R by Hadley Wickham, and he's a prolific R programmer and package publisher. So, so he's got some good stuff here. Okay, so here I've got a simple vector, okay, of just some numbers here, and notice that the value after the decimal refers to their placement in the original vector. Okay, so the first element is 2.1, the second element is 4.2, 3.3, and the fourth element is 5.4. Okay. And so you can subset a vector using positive integers, negative integers, logical vectors, or character vectors. Okay, so here you can just use subset and say, I want the third element and the first element, and it returns that. Okay. If you ask for order, it's going to say, what is the order in which I need to put these elements if I want them going from least to greatest? So order of X will say 1, 3, 2, 4. And then if you subset X using the order of X, it's going to print these out in least to greatest and say, oh, okay, the order goes 1, 3, 2, 4, and that goes from least to greatest. Here. Yeah, question?
So the order function automatically orders it, or it numbers it in order from least to greatest?
Yeah, So order tells you if you wanted to put these elements in order from least to greatest, what is the order that you need to do? You need to go the first element, third element, second element, fourth element is what it is, okay? So it's not a rank, it's the ordering, okay? If you put in the same thing, if you put in the same index, it's going to return duplicated values. So if you say subset vector x, but give me element 1 and element 1 again, it's going to give you the first element twice. No problem there, okay? And then if you give it something like this, 2.1 and 2.9, it just truncates those and it says, I don't really know what you're talking about, but I'll give you the second element both times, okay? And actually, it doesn't even give you a warning. It just says, here's the second element, here's the second element, because this is what you asked me to do. Okay. With negative integers, it's going to omit those elements. So here I put in x negative 3 comma 1, so it's omitting the third and the first element, and it returns this. Okay. You can't mix positive and negative integers because it doesn't know what you're trying to do, right? It doesn't know, like, okay, you don't want the first element, but you want the second element. What do you want me to do with the third and fourth elements? Do you want those or not want those? I'm not sure. So it says error, okay? With a logical vector, it's going to return things where it's true and leave out the ones that are false. So here, it matches them up, true, true, false, false, and it returns those, okay? And so this is often very useful when you say, when you create a condition and you say, give me x where x is greater than 3, x greater than 3, it's going to produce a logical vector, right, of trues and falses if x is greater than 3. And based on those values that are true and false, it returns back those elements. Okay, if the logical vector is shorter, then it gets recycled, right? So if you do true, true, false, what's going to happen? The true, false gets recycled to basically be true, false, and so it returns the first and the third element. Okay, and then a missing value in the index returns a missing value in the output. So that's something interesting, right? Okay, if you put nothing in there, it's going to return the original vector. So it's not too useful for vectors, but it's very useful for matrices because oftentimes you want to say, I want the third row, but I want all the columns. So you'll say, I'm going to subset and put in 3, comma, and then you put nothing, and it's going to return back everything, right? So nothing will return everything. And then if you do 0, it returns a 0-length vector, okay? A 0-length vector, which is very strange, okay? This is not missing data. It's a 0-length vector. So it's going to say, I've got a numeric vector of length 0. Okay. Okay, if the vector itself is named, you can use character vectors to return elements with matching names, right? So you can say, so here we're going to set the names A, B, C, D to these elements, okay? And you can say, okay, I want back the thing named D, C, and A, and it returns that as such. And just like anything else, if you feed it in multiple of the same, it's going to return those multiple times. Okay, and when subsetting with bracket, the names are matched exactly. Okay, so here I've named it A, B, C, and D, E, F, and I'm saying, can you give me back something with A, named A? And it's going to say, I couldn't find that. That doesn't exist. That's missing. Can you give me back something named D? No, I can't. That's what we've got. All right, with lists, we can subset similar to an atomic vector, okay? If you subset with a single bracket, it's always going to return a list. If you can also subset using double bracket and $, and you're going to pull out the elements out of that list. We'll distinguish that in a second here. So here I'm starting off with a list of 3 things, okay? And new numbers, okay? This is type double here, 1, 2, 3. A logical, true, true, and false, and then character vector here, okay? And here if I say, okay, give me back the first element, D bracket 1, single bracket here, it's going to just return back the first thing in that list, which is itself a list with the of only one item, and that's 1, 2, 3. Okay, so when I subset D with a single bracket, it's going to return a list, and this is what I get. Okay, so we'll come back to the double bracket and the $, in a moment here. Okay, with matrices and arrays, which have dimensions, we can subset these with multiple vectors, single vector, or with a matrix itself. Okay, so probably is the most common way of subsetting this is you supply a one-dimensional index for each dimension separated by a comma, and blank subsetting is now useful. So here we're going to start off with this matrix, okay, which is the elements 1 through 9 in 3 rows, okay? And here I'm subset it, saying give me back the first 2 rows, comma blank, which means give me back all the columns. So here I get the first 2 rows and all 3 columns, okay? And we can see that the third row is missing, which would have 3, 6, and 9. Here I can say give me back the rows, the first and the third, right? True, false, true. And give me back the columns that match the names B and A, okay? And so we can see it returns back the first and the third rows and the columns B and A in the order that I specified in here. Okay. And over here, what did I do? Return 0 of the rows and return everything but the second column. So it returns back this, okay, with nothing. None of our actual data. Yeah, this subsetting with zeros feels weird, but it works, okay? By default, okay, single bracket is going to simplify the results to the lowest possible dimensionality. All right, so if we do this, okay, what this means, if I look at A itself is a matrix, right? And if I say, whoops, is it a vector? It's going to say no, okay? But if I subset the matrix A to return just the first row, it returns this, okay? It's just the first row with named columns, but it's no longer a matrix. This is now a vector, okay? What it does is it has reduced it to a one-dimensional vector. You probably experienced this in Stats 20. When you subset something, like you just pull out a single column, you get now just have a vector of those values, right? I think you probably saw this, okay. So matrices are implemented as vectors with dimensional attributes. You can pull them out, you can pull elements out just as if they were a vector, okay? So if you say pull out, so here I use the function outer, which I don't know if you're familiar with, but it just basically does this. So here I've got a character vector with the elements, 1, 1, 2, 1, all the way through 5, 5. 25 elements in this thing. I can just say, give me back the 4th and the 15th element, okay? So the 4th element, it's counting down. It goes 1, 2, 3, 4. This is the 4th element. The 15th element, this is the 5th, 10th, This one's the 15th element, 5, 3, and it returns those. So notice I did not put a comma here inside the single bracket, right? There's a comma inside C to indicate I want the 4th and the 15th element, but I'm not subsetting using the comma to say I want 4th row, 15th column, okay? And so here it gives me back the 4th element and the 15th element, treating the entire matrix as a vector of 25 elements. And that's what we have here. Yes, question?
Sorry, what does outer do?
Outer does, it's like outer multiplication, but it's outer function applying. Basically, in this case, it's taking the vector 1 through 5, and it's saying, okay, line 1 through 5 up on your, I want to say rows first, and then 1 through 5 on your column. And then, using those two things, apply the function paste in this case, okay? Or what other function? The default function would be multiplication, okay? And it says take 1 and 1, paste those together. 1 and 2, and paste those together, okay? And in this case, paste is using the optional argument comma to separate them. But basically it lines these up. I can do, if I just did outer 1 through 10 and outer 1 through 10 here, what would this produce? This is going to create a matrix of 10 rows, 10 columns, and the default argument, its default function applies is multiplication. And so this creates my times table of 1 through 100, okay? And this is what we have. And then you can shortcut outer by doing %O%, and it does the same thing here. Outer is a neat function, okay? But the point of this slide was not outer, but to point out that you can subset one-dimensional, treating the matrix as a one-dimensional vector. Okay, you can always subset a higher dimensional data structure with an integer matrix, okay? Each row in the matrix specifies the location of one value where each column corresponds to a dimension in the array being subsetted, okay? So you can use a 2-column matrix to subset a matrix and a 3-column matrix to subset a 3D array. Okay, so what am I doing here? So keep in mind, I've got this matrix of 5 rows and 5 columns, okay? And here, I'm creating a matrix of basically that looks like this, okay? 1, 1, 3, 1, 2, 4, okay? And this says pull out the element where I want you to pull out 3 elements as indicated by 3 rows, and the coordinates of the first element are first row, first column. The coordinates of the second element is third row, first column, and then the coordinates of the third element I want is second row, fourth column. So we are basically, we are subsetting this matrix by giving it a list of coordinates. And we're saying I want the element at coordinate thing at 1, 1, 3, 1, and I forget what the last one is. Okay, so we can call out certain elements by their coordinates using it this way. So we're subsetting it using, in this case, a 2-dimensional matrix by giving it a column of 2 dimensions. Okay, and if you had a 3-dimensional array, you can give it a sheet of 3 coordinates with 3 columns, right? Play around with everything, okay, and learn this stuff. With data frames, we can subset the way we subset lists or the way we subset matrices, okay? And so here I'm creating a data frame that looks like this, 1, 2, 3, 3, 2, 1, ABC, okay? And here I can say, I want to subset the data frame using matrix notation. I give it kind of which rows I want. I want the row where the X column, df$x is equal to 2, but give me back all of the columns. So this gives me the row where X is equal to 2, and it gives me back all the columns there. here I say, give me back the rows 1 and 3, give me back all of the columns. So this is subsetting it just like we subset a matrix. Over here, I'm saying, I'm subsetting it the way I subset a list. I'm saying, give me back X and Z, okay? I could have done comma, X and Z, but I didn't. And why does it still work? Because now it's treating it like a list, okay? So keep in mind that the data frame itself is a list. In this data frame, how many elements are in my list? 3. I've got 3 columns. Those are my 3 elements in the list. And I'm subsetting, and I just want the X and the Z elements in that list. And it returns back the data frame as such, okay? If I want to select the columns like a matrix using the comma notation, I can do that, and I get back the same thing. Okay, so this is saying, give me all the rows where the columns are named X and Z. This one, it looks like it's doing the same thing, but there's no comma there to say, give me back the list where list elements X and Z. Okay. One important difference is that if you select a single column, okay, matrix subsetting simplifies by default, whereas list subsetting does not. So here I'm going to say, give me back the data frame where I selected just the column X, and if I ask the structure, we see that it preserves the data frame structure. Whereas if I said df comma X, so give me back the column X, we see it simplifies it to a vector form. Okay, so that is an important distinction when you're only selecting one thing. All right, let's see. Let's play this game of what's wrong. Okay, so here empty cars is some data from Motor Trend magazine. Empty cars. It's like a default data frame that just exists here. Okay, so back when you could buy the Datsun 710 or the Duster 360, I don't know what vehicle that was, but apparently it got 14.3 miles per gallon. Oh, and okay, so this is a data frame. It's got these columns: MPG, cylinder, displacement, horsepower, and things like that, right? The Honda Civic back in the day had 52 horsepower and got 30.4 miles per gallon. So we probably made some progress in vehicles. This is like an old data set, and if we look at the structure of cars, we see we've got 32 observations of 11 variables, and this is what we have. And everything is a numeric vector, which is, or numeric data type, which is nice for us. Okay, so if I say empty cars cylinder equals 4, what's wrong with this? Or what am I trying to do? I want all the cars where the number of cylinders is equal to 4. The problem here, we need double equals, right? To test for equality. Single equals is for assignment, double equals is to the test for equality. And when I do that, now I get back all the cars where the number of cylinders is 4. Okay. All right, what's going to happen here? So, here, I'll just show you what would happen. So if I tried to subset empty car, look, -1 through 4, what happens when I type in -1 through 4? It does that. So if I tried to subset empty cars like this, it's gonna complain. Okay, you can't mix that. I could have done this. Maybe this is what I wanted to do. Okay, so this will return everything but the first 4, and then this will return just the first 4. So maybe I'm not quite sure what we wanted to do here. If we didn't want the first 4 rows, I should have put the negative in parentheses around here. Okay, over here, cylinders less than or equal to 5. What's going wrong here? basically I don't have a comma here, okay? So what I want are all the rows where this is less than or equal to 5, which is going to give me that. Okay, if I get rid of this comma here, what this part does, okay, so notice what this part's doing, it's going to give me back a vector of falses and trues. That part is fine, except I only have 11 columns, and this vector has 32 elements in it. So if I gave it a vector of 11 true and false values, 11 logical values, it would work. It would just give me back. So if I said, you know, if I took this thing and I just said, give me back the first 11 elements, and then I fed this into empty cars, then this would work. This is not what I want, but here it's giving me back, I gave it a vector of 11 true false values, and it looks at, okay, you want the third column and the, what is this, 8th and 9th columns, okay? So it's going to give me back just 3rd, 8th, and 9th column, which is 3rd, 8th, and 9th column, which is what it does. But I don't think that's not what we want it to do, right? So don't forget to use the comma here when you do it here. Okay, over here, I want cylinders equal to 4 or 6. This that's going to give us a problem. What we need is for this vertical bar, meaning or, I have to say I want cylinders equal to 4 or cylinders equal to 6. Okay, and that will give me back all the rows where the number of cylinders is 4 or 6. Okay, 1 through 20. What this is going to do is it's going to try to give me back. Over here, if I ran this, it would give me back the first 20 columns, and it's going to say, well, I only have 11 columns, so that's a problem. Well, if I want just the first 20 rows, I got to put the comma there. Otherwise, it's not going to work. Okay, this is important. The double bracket, okay, can be used for lists, okay, or and thus data frames. Double bracket and $sign. Double bracket is similar to single bracket, except it can only return a single object, and it pulls the pieces out of the list, okay? And then the $sign is like using the double bracket, but it uses the character subsetting, assuming things are named here, okay? You need to use double bracket when working with lists, or you're gonna want that, because when you use single bracket, it's always gonna return type list, okay? So think of a list as a train, okay? And if you say, I want single bracket 4 through 6, it subsets the train and it pulls out train cars 4 through 6, okay? Whereas if you use double bracket 5, it returns the objects that are stored in train car number 5, okay? So double bracket returns the object inside that train car, okay? Whereas single bracket returns the train car itself, okay? So if you say, so 4 through 6 will return a train using cars 4 through 6, whereas the double bracket can only return one of those things, and it's going to go into the train itself, okay? So because it can return only a single object, you must use double bracket with either single positive integer or a string. So here I've got a list of A and B. If I use double bracket of 1, it's going to return back the object 1. If I used single bracket, what would it do? I can't even highlight here. It would return a list where it's going to say list A equal to 1, right? Or A1. And then double bracket here is this is what we have. Okay. When you subset, a lot of times it simplifies these things. So we saw this when we subsetted the matrices. It simplified from matrix down to a vector, things like that. If you want to preserve the original structure, then you can use drop equals false. I'm going to run out of time here. But this is what we have, okay? So when you simplify with, like, you can apply this for vectors, okay? Basically, doing this for vectors will drop names and things like that. And if you want to preserve the original structure, you can do this. Check this out in the reading here, okay? And so I'll post these notes up and kind of flip through these slides here. So atomic vectors returns names and all of this stuff we've got. Let me just cycle through here. Okay. Yeah. Okay. We'll end here for now, and we'll continue on Thursday. We'll pick up on some programming stuff. I'll post up all of these notes. Some of it, obviously, I had to skip over some of this stuff. So make sure you spend some time tonight and tomorrow going through the notes and the material I was not able to cover. I'll also post the first homework assignment, and you can take a look at that as well. Okay, we'll see you guys on Thursday.